Welcome everyone to another edition of the GEOTOP-A seminar. And today with us we have Mathilde Papillon, who's a physics PhD student at the Geometric Intelligence Lab at UC Santa Barbara. And she will tell us about how to make any GNN go topological with TopoTune. Now, before you start, I just wanted to say that Mathilde has extensive experience in modeling different sorts of physical phenomena, including dance and sports, and using artificial intelligence in the guise of topological deep learning to understand these different activities. And she's been basically a driving force behind the development and implementation of a lot of these ideas from topology and from algebraic topology into deep learning systems. So it's a very great pleasure for me to be able to introduce her. I think this is somewhat of a nascent field from the perspective of topology and algebraic topology, but at the same time, a very well-established field from the perspective of computer science and AI, because that's a very fast-paced moving field. So I think this is a wonderful opportunity for these communities to start interacting a bit more as well. And thank you very much, everyone, for being here. And please go ahead, Mathilde.
Thank you, Pablo, for the introduction. I'm just going to start off by saying if anyone has questions or wants to stop me, that's totally fine. I just can't see the chat while I'm presenting, so someone will just have to sort of interrupt me because I won't be able to see that. Okay, I am Mathilde. I am a graduate student in the Geometric Intelligence Lab at UC Santa Barbara. Thank you so much for having me. I'm really excited to be here. As Pablo said, I'm very much from the deep learning world. My background is in physics, but all of my graduate studies to date have been very focused on the really computational math, sort of deep learning side of the field and not so much the mathematical side. So I'm really excited to start interacting with all of you. And today I want to tell you a little bit about a recent research project that we put out on arXiv last year called TopoTune. And I think this is a really cool sort of small test case of topological deep learning that might have really broad ramifications for the field. So I'm going to just give a quick overview of what I want to talk about today. First, I'll start with my definition of topological deep learning. This has been sort of more and more confusing question to ask as the field is emerging and there's a lot of different techniques being proposed. It can be hard to know what the word topological means at this point. When I talk about topological deep learning, I mean really algebraic, discrete topology and using higher order relationships induced by this algebraic, discrete, combinatorial topology to increase the performance of graph neural networks. So we're talking about message passing neural networks that use discrete, higher order connectivity. And I guess I'll go over that a little bit more in detail during the background section, but I just want to give a PSA. There is other forms of topological deep learning out there that use things like topological data analysis, persistent homology, that kind of stuff to encode the topology of a network, but that's not so much what I am interested in. Okay, so once we go over that, I'll talk a little bit about challenges facing this branch of the field and how this work addresses those challenges. So the work proposes a theory, meaning a new type of model, a new type of neural network, and an implementation. And with that, we have a lot of really exciting results that I'm excited to show you. Okay, so I mentioned graph neural networks earlier. Just in case you haven't heard of one of those before, they're one of the most popular architectures in deep learning today. They came out in about 2017, and it's just been nonstop activity since then. So in a graph neural network, we have these layers. In this little cartoon, I have 3 layers. And what these layers do is this process called message passing, where we are updating the features of the nodes and the edges of a graph. And maybe a way to visualize that message passing process is to imagine colors, for example, features on the nodes. And during message passing, those colors will circulate in the graph according to some connectivity that in this case is described by our edges. And that will result in some new set of updated colors, right? Updated features. And we keep going. We do this process until we get to a stable representation and we get a prediction out of it. So we can apply this process to all kinds of data sets and from the real world, like social networks and molecules. These are graphs, right? They're nodes that are connected by edges. However, these are also really not just pairwise relationships that are describing this fundamentally important property of my graph. For example, if I just have access to nodes and edges, can't represent the fact that my molecule here has rings, right? Those edges aren't enough to tell me that there are rings in my molecule, which are fundamentally important properties of the molecule that will alter its purpose. Similarly, in the social network, I can't, with just edges, describe a group of friends that might have something in common. So we're missing out on important fundamental properties of our data when we're constrained to pairwise relationships. And that's how we get to topological neural networks, which we say generalize graph neural networks by representing higher order relations. So just coming back to what I was saying earlier about the kinds of topology that we're interested in, here we're going to use algebraic topology, combinatorics, to represent complex connectivity in the graph that goes beyond pairwise relationships. And that's kind of the extent of the topology that we're interested in here. We're talking about just higher order relations induced by some more complex algebraic topology. Okay, so what does that actually look like? Well, if we come back to our cartoon from earlier, this is what a topological neural network looks like. So instead of a graph, now we have some complex, right? Some cell complex, combinatorial complex of some kind that has more intricate relationships. Some of them are pairwise, some of them aren't. There's a coloring of those relationships, which means something that we'll get to later. And we are doing the exact same thing that a graph neural network would do. We're doing message passing between the features, right, between the nodes, the cells of that complex, and we ultimately achieve some representation of the complex at our last layer that we will then extract a prediction from. So a topological neural network fundamentally looks a whole lot like a graph neural network. We just say that the domain has changed. It is no longer a graph. It is now some more complex, higher order complex. Okay, so I just mentioned the word domain. Let's define that more explicitly. When we talk about the traditional discrete domains in deep learning, we think about sets. So maybe you've heard of PointNet, for example, and graphs, which are the domains of graph neural networks. In topological deep learning, we have now access to this whole slew of new domains which leverage higher order relationships of different kinds. So we have on the left part-whole relations, which induce some very strict geometrically constrained higher order relationships. So in a simplicial complex, which you would have heard of if you've ever worked with meshes, for instance, we can add triangles to our graph, basically. We can now add cells of higher rank, so cells that are not nodes and edges, but that are faces or volumes and so on, that are bounded by really specific rules. So they can basically only be triangles, for example, in the face case. For the cellular complex case, we now have access to a little bit more flexibility, and we can have different kinds of faces and different kinds of volumes that aren't necessarily triangles. That's part-whole relations. Set type relations, instead of inducing this like really rigid geometric hierarchy in our complex, instead of that, we now have a very flexible set-wise, n-wise relationship that we call the hyperedge, which you might have heard of. A hyperedge can connect any amount of nodes in any possible way and allows us to have this really great flexibility at the edge level. So we're not adding faces and we're not adding volumes, but we are sort of infinitely flexible with our edges. And finally, the belle of the ball, the combinatorial complex, is the most general domain of them all because it combines both part-whole relations and set-type relations. So you now have access to these very flexible hyperedges at both node, edge, face, volume, and so on and so forth. So we can basically do anything we want and have any hierarchy we want. And it turns out that this combinatorial complex is really useful for a lot of real world cases that are a little bit more complex. And I want to talk about real world cases. So let's look at some examples of what these domains look like when we apply them to data sets. So the part-whole relations, as I was saying, are really good for geometrically constrained data. So coming back to our example of a molecule, your nodes could be atoms, bonds or edges, and rings can be faces. I also mentioned that a simplicial complex is a mesh. So we have an example of that. In the hypergraph case, now we can think about things like interaction networks. So in a protein interaction network, the interaction between my proteins A, B, G, and F isn't necessarily more important or bounded by another interaction. All the interactions are kind of at the same level of importance, if that makes sense. So it's really useful for us to be able to tie any protein together in any hyperedge and describe all the interactions that are possible without having this notion of one interaction being bounded by others, for instance. And then in the combinatorial complex case, we can imagine having a molecule that has the geometric constraints that are best described by a cellular complex, for instance, but then also wanting to highlight functional groups within the molecule, such as the amino acid in the molecule or the carboxylic acid. And for those functional groups, hyperedges are really useful because they're not constrained by the geometry of the molecule at all. So hopefully that gives you some motivation as to why these domains are useful. And hopefully that kind of sets the scene for the topology that I'm talking about in topological deep learning. I think there's obviously a lot of progress to be made in terms of connecting this field back to all the great work that topologists have been working on for centuries. And Pablo's been really great for that. Thank you, Pablo. And we're really excited to build upon this sort of foundation of algebraic topology in graph neural networks. So moving on to another really important ingredient that we need to do topological deep learning. I call them neighborhood structures. So here on the left, I have a cell that is, in this case, a simplicial complex, right? It's got nodes, edges, and triangular faces. I mentioned this concept of rank before. A cell of rank 0 is a node, a cell of rank 1 is an edge, a cell of rank 2 is a face. And to be able to do message passing on this complex, it's really important that we define our connectivity, which cell we consider to be connected to which cell. In a graph, this is fairly simple. You just have your edges, right? Your edges tell you which nodes are connected to which nodes. Here, we have more options because we don't just have edges. We have all kinds of different possible connectivities, and our neighborhood structures are what will tell us is the connectivity. So there's 4 like standard neighborhood structures that people use a lot in the literature. You could have any neighborhood structure. There's maybe not an infinite amount, but there's a very large amount of possible neighborhoods that you can choose from. I'm just going to show the 4 that people typically use. They're called upper adjacency, lower adjacency, boundary, and co-boundary. Upper adjacency is perhaps the most vanilla of them all because it is what we use in a graph. So upper adjacency is when we consider the nodes and the edges and any cell that is adjacent to another cell through some higher order cell. So that was a lot, but let me rephrase. Our nodes, for example, our blue nodes here, are upper adjacent if they're connected by an edge, and our edges are upper adjacent if they're connected by a face. Our faces cannot be upper adjacent because there is no higher order object, there's no volume, for example, for them to be upper adjacent through. So that's our upper adjacency in this case, is the combination of our node adjacency and our edge adjacency. The lower adjacency is the same thing, except instead of going up a rank, we're going to go down a rank. So our edges are lower adjacent if they are connected through some shared node, and our faces are lower adjacent if they're connected through some shared edge. Nodes cannot be lower adjacent because there's no lower rank that they can be connected through. So those are our adjacencies. Boundary and co-boundary is incidence. So maybe you've heard the word incident before. In this case, we're considering which cells are incident to the rank that we're considering. So the boundary of the edges is all of the nodes that are incident to that edge. And the boundary of the faces is all the edges that are incident to that face. So the whole boundary of the complex is the ensemble of the nodes and the edges that are incident to the edges and the faces. Co-boundary is the same thing, except instead of going down a rank, we're going to go up a rank. So the edges that are incident to nodes and the faces that are incident to edges. That was a lot. Just to recap, we have defined 4 neighborhood structures that tell us something about how we could consider the cells in our complex to be connected. Just like I want to know which nodes in my graph are connected, now I can describe how my edges are connected and how my faces are connected in my simplicial complex. Okay, so now that we have this sort of essential ingredient, we can talk about message passing in a topological neural network. So message passing, as I was saying at the very beginning, is what happens in one layer of my neural network. So HT here, we can call on the left, we can call the feature on a cell X at layer T. And all the steps that we're seeing after that are what happen in that layer. We're going to define 3 arbitrary neighborhood structures, N1, N2, N3. In this case, a set of nodes, a set of faces, and a set of edges. And during message passing, we have these steps. So each member of each neighborhood, N1, N2, and 3, is going to send a message to the receiving node. And by sending a message, I mean send the feature that they're carrying times some learned parameter, probably. It could be anything, but that's typically what it is. Once that message is sent to the receiving node has to aggregate all the messages from that neighborhood, right? So in the case of N1, we have to aggregate the messages from our 3 nodes, N2, 3 faces, and 3 edges. So now we have 1 message per neighborhood. The next step is aggregating each neighborhood specific message. So we have 3 neighborhoods, 3 messages. We're going to aggregate them once more through some aggregation function, could be anything. And then finally, we will send this final message through some update, possibly that is dependent on the original feature HTX. And that's how we land on HT+1, so our new layer, our new layer's feature on X. So that is what happens in one message passing layer of a topological neural network. we have our neighborhoods, everyone sends a message, we aggregate in the neighborhood, and then we aggregate all the neighborhoods, and then we have some updated final feature. Okay, so that's one message passing layer of a topological neural network. This is the cartoon that I showed earlier. The process I just described is what happens between two of these complexes. That's how we update the features. So this process happens for every single cell in my complex. So if I have features on my nodes, features on my edges, features on my faces, we're going to repeat this process for every single cell. That is one of the problems with topological deep learning. As you can imagine, it gets pretty expensive. So we'll talk about that later. Great. So hopefully this has given you kind of a good taste of what a topological neural network is, how we define it, what happens during training of a neural network. And now we can talk a little bit about challenges and issues that make this field maybe a little bit less appealing for practitioners. So the first challenge is the research landscape. Pablo mentioned that this field is quickly emerging, which is very much true. It's quickly emerging to a point where notation has not really been agreed upon by the community. So there are all these papers coming out, each of them proposing a new topological neural network, and they all use a lot of different notation. They don't necessarily use the same software. Everyone is kind of writing software from scratch every time, which can be really difficult to actually use for a practitioner. And we're always picking one domain at a time. So for example, I will study one hypergraph neural network or one simplicial neural network, and it can make it really difficult to know which domains are good for which applications, and do any sort of cost-benefit analysis. I think it is normal and good for such a young field to have so many papers that are exploring different things without necessarily always comparing themselves to the rest of the field. Benchmarking can be really burdensome. However, it's made for a very fragmented research landscape that doesn't necessarily use all of the advances at its disposal. Because if those advances are written in a different notation or in a different software, it can be hard. So that's challenge one. Challenge two is the disconnect from the GNN field. So if you've worked with graph neural networks before, I'm sure you've heard of PyTorch Geometric or Deep Graph Library. These are very well established, very well tested packages that allow for really easy manipulation and easy implementation of graph neural networks. Unfortunately, topological deep learning isn't there yet. Its software is much younger and much less well established and tested. And unfortunately, it's very isolated from this from this graph neural network software. So it's hard for me as a practitioner, if I'm very used to using PyTorch Geometric, for example, to apply those skills, apply that knowledge to topological deep learning. I kind of have to start from scratch. The other thing that's unfortunate is that previous works that have studied graph-based TDL are pretty limited. So there are researchers specifically at NeurIPS of 2023 that asked the question, well, how can we make topological deep learning graph-based such that we can leverage all these advances in the graph world? But the architectures that were proposed there don't actually replicate TDL computations. They collapse a lot of the topological information by creating these Hasse graphs, like you can see on the right there, that represent every single cell as a node and every single connection between those cells as an edge. It works okay, it works well, especially for certain properties that we care about, such as expressivity of the neural network, but it doesn't actually simulate perfectly a topological neural network, and it loses a lot of other properties, such as generalizability and equivariance, if that means anything to you. All that to say, we're pretty disconnected from the GNN world, which is unfortunate because the GNN world is much better established. And we don't really yet have a good bridge between topological neural networks and graph neural networks. Okay, challenge 3 is building models that work across domains. So currently, if I have a data set, right, and it's a graph-based data set, but I think that there are higher order relationships that are important, it is my job as a practitioner to figure out how to test it in the different domains. So if I want to test it as a simplicial complex or test it as a cellular complex, I have to go and get a model that has been trained for that domain specifically. I can't just take one model and try a bunch of different domains, which is unfortunate because a lot of that sort of hard-coded information about our data sets is not necessarily domain specific. I don't necessarily know off the bat if my data is a hypergraph or a simplicial complex, right? So that's something that could be really useful and that we wanted to tackle. Okay.
So, there's a question in the chat that might be
Yes.
relevant for this point. Rolo is asking, this happens because of data structures implementations or because some theoretical point of view?
This happens, sorry, about the models that don't work across domains?
I guess that's what the question is referring to.
Okay.
In case Rolo wants to clarify, but yeah.
Yeah, it happens for a few reasons. So from a theory side, kind of like what I was saying in challenge 1, up until now, people have, when they build a topological neural network, they only really think about one domain and will write the notation in that domain and do their calculations of expressivity, for instance, with respect to that domain. So how expressive am I compared to other cellular neural networks or other hypergraph neural networks? The theory machinery isn't really developed to work across domains. So that's a theoretical reason. A practical reason is that up until very recently, there hasn't been one software, one available open source package where you have access to a bunch of liftings, which are the processes that transform a graph into a higher order complex for multiple domains. So if you were interested in trying to lift your graph data set into a cellular data set and then train a neural network on that, you needed to figure out how to run a specific software that could do that. But then if you wanted to do the same thing for a simplicial case, take your same data set, send it into a simplicial complex, you had to go and find another software and repeat the whole process in some other package somewhere else that's different. There wasn't a way for you to try different liftings in one spot, implemented in the same spot on one data set. And there's actually some people in our lab, Guillermo and Lev Telyatnikov, who's joining our lab imminently, that last year they did something very, very difficult. And they implemented a bunch of liftings, and they actually hosted a challenge at ICML to crowdsource more liftings in one spot. So now using their code, which is called Topo Benchmark, and which I'll talk about later, you have access to all of these topological liftings that can test a bunch of different domains in one spot, which makes it way, way easier. And with TopoTune, which I will get to, we provide a solution to some of that theoretical machinery issue that I mentioned earlier. Does that answer your question?
It was in the chat, so like,
okay. Great, thank you. Okay, so hopefully that gives you a taste of the challenges facing the field and will motivate this work, which I will go over in 3 steps. So the theory, the model that we're presenting, the implementation, and some results. Okay, This is the paper itself. It is on archive currently, so feel free to go read more if you are curious. Our purpose in the work is to address the challenges facing TDL. So we propose a model that generalizes and subsumes all the current research in topological deep learning, all the current existing models in the field. Our model connects TDL back to GNNs so that we can leverage those advances and leverage that software. And our model works across topological domains. Our model is called Generalized Combinatorial Complex Neural Networks. So maybe you'll remember from my little introduction to TDL that combinatorial complexes are the most general domain of them all. So if you can get a neural network to train on combinatorial complexes, you have automatically access to simplicial complexes, cellular complexes, and hypergraphs, and anything else, really. We have two important sort of new ingredients that didn't exist in TDL before. And I want to go over those ingredients kind of slowly because I think they're really interesting and they are at the heart of why our model can do all of these new things. So the first important ingredient that we propose is a new expansion method, a new graph expansion method that allows us to write a complex, so in this case, this simplicial complex, in a way that is more robust and captures more of the topology than previous works. We call this graph expansion an ensemble of strictly augmented Hasse graphs, which sounds like a lot, but all it is that instead of writing our combinatorial complex, in this case a simplicial complex, in terms of one Hasse graph, which is what previous works have done. So just to recap, in this case, we are writing each cell of our complex as a node, right? There are blue nodes, pink nodes, and purple nodes, and we are encoding the neighborhood relationships between these cells as edges. So instead of writing our complex as one graph with a bunch of edges in it, we are going to write it as an ensemble of Hasse graphs where we are reserving one Hasse graph per neighborhood. So before, I was having all of my neighborhoods collapsed into one graph. Here, my adjacency and my boundary is collapsed into one graph. Now, I have two graphs, one that is dedicated to adjacency and one that is dedicated to boundary. So that's the first cool novelty here. The second thing is per rank neighborhoods. So in the past, in topological deep learning, when I talk about the adjacency of the complex, that necessarily encompasses both the adjacency of my nodes, the adjacency of my edges, the adjacency of my faces, so on and so forth. It is not rank specific. When I talk about adjacency or boundary, I have to include all of those different ranks. In per rank neighborhoods, that is not the case. So I'm allowed to talk about the upper adjacency of just my nodes, or the lower adjacency of just my edges, or the lower boundary, right, of just my edges. I don't have to include all of the ranks every single time. And that will help us cut down on computational costs pretty significantly, as I will show you later. Okay, so those are the two important novelties that generalized combinatorial complex neural networks use. Now let's look at what this model actually is. So this is sort of the overview figure that I want to break down. In a GCCN, we send in a complex, right? Again, I have this toy simplicial complex. And the first thing that happens is that we break it down into an ensemble of strictly augmented Hasse graphs. So if I have three neighborhoods, I will have three graphs, right? One graph for N1, one graph for N2, one graph for N3. And once I have my three graphs, each of these graphs will be sent into a dedicated GNN. A normal vanilla standard GNN, nothing fancy, just what we're used to, which is nodes passing messages between edges. That's it. Once my GNN has mixed around my node features, right, through my edges, I recover those new features and I repopulate my complex with them. So in this case, N2 and N3 are both proposing new features on the edges, right? They're both outputting a new set of features for the edges of the complex. So I will simply aggregate those. And now I have a fully new set of features, which is that cartoon between C and B, like the bright green edges, that has populated my complex. And I can repeat this process, basically one graph, one Hasse graph at a time in a dedicated GNN. And this might look a little bit hacky, but the reality of the fact is that we have perfectly replicated the computations of a topological neural network by collapsing only one neighborhood at a time into a graph and then proposing a dedicated GNN to each of those graphs. We have not lost any topological information. This is not a compromise. It is a topological neural network. And what's really cool is that because its machinery is fully sort of supported by GNNs, we can build this using GNN software. We can simply stack GNNs from PyTorch Geometric or Deep Graph Library and create a robust general topological neural network with any GNN, which is the title of this talk. So hopefully that's a little bit exciting. I know I'm making a lot of bold claims and all you're looking at is a cartoon, but hopefully I'll go over some results and convince you. I also suggest that you take a look at the paper if you want to read more about the proofs that show that this is, in fact, a topological neural network. Are there any questions before I move on? Sometimes all these claims can generate questions. No? Okay, great. Okay, so I'm going to keep going. Coming back to my explanation of what a message passing layer does, remember this is how we described a topological neural network. This is what happens in a topological neural network. I have matched each of these steps in this cartoon, A, B, and C, to the steps in my GCCN. So my point here is just that every single step that normally happens in the message passing scheme of a TNN, we can find in a GCCN. The aggregations are just a little bit funky, but it boils down to exactly the same thing. Okay, so theoretically speaking, GCCNs formally generalize existing topological neural networks, meaning that every single existing topological neural network is either a special case of a GCCN, is a special case, and then GCCNs also provide new options that we didn't have access to before, specifically because of the per rank neighborhoods. GCCN layers are what we call permutation equivariant, meaning that if you relabel the cells in your original complex, the result will be equivariant to that relabeling. This is a property that topological neural networks have, so it's important that GCCNs maintain them. In previous works that do graph-based simulations of TDL, they collapse too much information and do not retain this property. So retaining this property is a big win for us. And expressivity, GCCNs are provably more expressive than existing topological neural networks, meaning that they are either as expressive, which you would expect to be the case if existing topological neural networks are a special case of GCCNs, or more. And that is due to the increased flexibility we get from per rank neighborhoods.
Just a quick question. Maybe you could explain the concept of expressivity for people that are not familiar or
Absolutely. Yeah,
practitioners,
absolutely.
because you've mentioned it a couple of times, but maybe
Yeah,
not
no,
everyone
definitely.
knows exactly what that means.
No, thank you for that perspective. Like I said, I'm from the deep learning world, so these are terms that I forget to define. So expressivity, specifically in our field, we like to think of as the power to distinguish graphs or the power to distinguish complexes. If I show your neural network two graphs that are maybe not exactly the same, but similar looking, can it distinguish them? Is it able to classify them as different? And it turns out that there are different levels of that distinguishing power. And we have tests, specifically the Weisfeiler-Lehmann test, if that rings any bells. We call it the WL test. That can help us determine to what extent your neural network is provably powerful in distinguishing two graphs or two complexes. So higher order WL tests were one of the big advances in TDL a couple years ago, 3 years ago. And since then, that's how we compare ourselves to each other in terms of determining who's more expressive. I will say, and you can read more about this if you're interested, there has been a growing critique in the community, not just in TDL, but also in graph neural networks, about the WL test, meaning that it is it's a very pretty and elegant and mathematically robust test, but it might not actually be that useful for real world scenarios, and that we might want to start considering new ways of measuring expressivity. So that's kind of an ongoing conversation in the field and something that I expect will change in the next few years. But for now, that is how we define expressivity. And when I say that GCCNs are provably more expressive, that's because we've run WL tests that are provably more powerful than existing tests.
Thanks a lot. I hope that helps everyone. Yeah.
Yeah, awesome. And you can read more about WL tests. This is like a really recurrent theme in the field, and there's a bunch of really great blog posts about it online. Okay, so implementation-wise, I mentioned Topo Benchmark. TopoTune, which is the lightweight PyTorch module we propose to run GCCNs, is hosted inside Topo Benchmark. Topo Benchmark is a very, very exciting project because it makes all of the models, or all of the popular models of TDL and all of the popular liftings of TDL and all of the popular data sets of TDL available in one spot. So for the first time ever, designing, running, training a topological neural network is as simple as defining a configuration file. And that's really exciting for the field because up until now, you've had to just rebuild the wheel every single time. It's been pretty difficult. So I'm really excited about this project. It was a lot of work, and I think it's really exciting that our work is now hosted inside of Topo Benchmark because it means that running our work is equally as simple in terms of just defining a configuration file and picking any data set you want, any domain you want, any lifting you want, so on and so forth. Okay, so that was my little spiel about Topo Benchmark and how cool it is. Definitely go check it out on GitHub. This is what Topo Benchmark looks like. It is very modular and allows you to pick any data set that you want, any neural network that you want. And when you pick your neural network, you get to pick your encoder, your backbone, your readout, so on and so forth. There's a bunch of like pre-implemented defaults, so you don't actually have to pick all of these things every single time. But it makes it really cool because you can very easily customize your choice of topological neural network and the training scheme you want to use. TopoTune is just a new choice of backbone, of neural network backbone. TopoTune allows you to simply pick GCCN as your backbone model, and it allows you to pick the parameters of your GCCN. So specifically, what GNN are you interested in using? For example, you could want to use this very popular GNN called GAT, one of the first basically attentional GNNs. And you can pick the neighborhoods that you're interested in using. So for example, maybe your upper adjacency of your nodes, your lower adjacency of your edges, and your boundary of your faces. So those are the three neighborhoods that I've picked. And finally, you can pick your domain. And like I said, this is kind of a big deal that you can just pick whatever domain you want. To my knowledge, it's the first time that choice of domain is just a hyperparameter and not a fundamentally baked in, built-in property of your code. So that's it. That's how you design a GCCN, and then you click play, and Topo Benchmark takes care of the rest, which is really exciting. And in our case, we ran this experiment about 55,000 times because we wanted to test a whole lot of possible GCCNs. So we considered all of these different models. We considered GAT, GCN, GIN, GraphSage, which are all pretty vanilla, standard, like very popular GNNs, as well as Transformer. Transformer is kind of interesting because it is not a message passing architecture. So when we use a transformer applied to our Hasse graphs, we are collapsing some information, right? A transformer will let everyone talk to everyone. There's no constrained adjacency. So that's not quite a normal topological neural network, but we wanted to throw it in there and see what would happen. We considered two domains, the simplicial complex and the cellular complex. And we also wanted to test whether or not our proposed graph expansion was as useful as we thought it would be, meaning that we tried our graph expansion, which is one graph per neighborhood, and the traditional graph expansion of sending the whole complex into one graph, which I mentioned previous works had done in 2023. And then this is the neighborhood structures we considered. So we considered 10 neighborhoods, possible neighborhoods, and some of these are per rank, meaning that they are only they can only be described with per rank neighborhoods, and some of them aren't, meaning that it is the whole adjacency, it is the whole boundary, so on and so forth. So you can do quick math and figure out that we ran a ton of different possible GCCNs, and we also ran them all on a bunch of different data sets. So this is kind of like a massive sweeping benchmarking type of experiment. And I'm really excited about the results. So let's break down this big table before I throw a bunch of numbers at you. We are interested in comparing GCCNs to the best available topological neural networks. So Topo Benchmark ran a bunch of the most popular topological neural networks on all of these data sets. And the rows that I'm showing you right now are the best available model, the performance of the best topological neural network out there for each of these data sets in each of these domains. I mentioned that we tested two domains, so the cellular domain and the simplicial domain. We still include at the bottom there the performance of the best topological neural network on the hypergraph domain, because it turns out that the hypergraph domain is really useful for certain data sets, and that was the best performance available in Topo Benchmark. So hopefully this table sort of makes sense before I fill in some of the numbers. On the left-hand column, you can see all of the different GCCNs that we tested, basically the different GNNs that we made topological. The bottom row of the cellular domain and the simplicial domain is the performance of the best GCCN using only one augmented Hasse graph. So that's how we are going to compare our performance against the performance of the previously available graph expansion. So let's just fill this in and break down some of the results. So it turns out that in 11 out of the 16 data domain combinations we tested, GCCNs outperform the best currently available topological neural network. This is really exciting because we barely did any hyperparameter tuning. We kind of just threw all of these different GCCNs into Topo benchmark without modifying any of the default hyperparameters during training. And just like that, sort of kind of at random, beat the majority of available topological neural networks. And I think that speaks to the usefulness of the GNN field and how much we've been missing out in terms of not using those existing GNNs into in topological deep learning because they do really well. And what's kind of interesting is that different topological neural networks do well with different graph neural networks do well for different data sets. So that's kind of exciting. The other thing that is cool is that we find that the single augmented Hasse graph, so the previously available graph expansion method, only provides comparable results in 3 out of the 16 cases. And in all of the other cases, our method does better. So this kind of speaks to the theoretical intuition that not collapsing topological information is helpful and leads to better performance. So that's kind of like the big flashy table of our huge benchmarking experiments. We also wanted to point out that the model sizes of GCCNs are often smaller, sometimes much smaller than the best available topological neural network. And this is because we have access to per rank neighborhoods. So I can sort of cherry pick the neighborhoods that I'm interested in and significantly reduce the amount of parameters in my model versus in a traditional topological neural network, you can't do that. If you want adjacency, you have to have all of the adjacency. If you want boundary, you have to have all of the boundary, which leads to greater parameter sizes. So that's kind of exciting. These are just like some highlighted examples of much smaller models that achieve better results. The other thing that we tried was improving upon existing models. So can we look at existing topological neural networks, replicate them inside the GCCN framework, and then improve them by replacing their message function with GNNs. So instead of using sort of the hacky from scratch message passing function that is specific to that model, what if instead you use GAT or GCN or GIN or GraphSage? So again, the rows that I'm showing right now are the result obtained by Topo benchmark when they test these models on these data sets. When we do the exact same thing, except with a different message function, we sometimes obtain better results, which is kind of exciting. This is like a really simple modification that we've done to the model and immediately have gotten access to, in some cases, significantly better results. And what's kind of interesting here is that the ensemble of strictly augmented Hasse graphs, our graph expansion method, doesn't seem to be as useful in certain cases, meaning that collapsing all of the neighborhood information into one graph seems to be sufficient for certain cases, especially the node level tasks. So more work needed to understand why that is the case. Okay, so yeah, these are just some of the examples of places where we perform better just by replacing the message function. The last result that I want to talk about is lottery ticket models. And this is really cool. Basically, we find that we can maintain performance, meaning be within a few percent of the performance of the best model on a data set, while minimizing model size, just by considering different choices of GNN and different choices of neighborhood structure. So, for example, in the protein case, I'm showing models that are 50% the size of the best performing model, but perform 99% as good. And that's just because we chose the right neighborhood structure and the right GNN. So I think there's a lot of work to be done here in understanding the importance of choosing model, choosing neighborhood structure and choosing your GNN model. Clearly, for some data sets, you can land on a lottery ticket combination that has really good performance and really small model size. So lots of work to be done here, and I'm really excited about it. Okay, so GCCNs, in conclusion, allow any GNN to be topological in a robust way. They generalize the current model landscape, they leverage GNN advances, they work across topological domains, and they are easily implemented with just a single configuration file, and easily iterated over using TopoTune and TopoBenchmark. So with that, I am going to conclude, and thank you so much for listening. And if there's any time left, I'm happy to take questions.
Well, thank you, Mathilde. That was fantastic. So anyone who has a question, feel free to open your mic or write it down in the chat. Does anyone have anything that they would like to ask Mathilde right now? Okay, so maybe I would like to know, Mathilde, like what current applications could you explain to the people here so that they could have like a, I don't know, a grounded example just of a single thing that
For
that you
sure.
could exemplify some of this, maybe as a first question.
For sure. I'm really interested in human movement. So when you think about representing the human movement to a computer, you can have the nodes be your joints and the edges be your limbs, right? Like just a skeleton. But when we move with correlated joints, right? Your leg is moving as a correlated unit. Your arms are moving as correlated units. So I'm really interested in representing human movement with these higher order interactions, in topological neural networks. But the problem is that human motion data sets are enormous. They're massive, massive data sets. And your computer will melt if you don't figure out a way to cut the parameter size of your model. So I think TopoTune will be really useful for that.
Excellent. Yeah, I'm looking forward to those exciting applications in both art and sports. That'll be very exciting to see as they develop. And maybe just to comment, because I mean, I've seen this from seeing you work at the Geometric Intelligence Lab. I know that the amount and breadth of experiments that you carried out was really enormous. And I guess, do you have any sort of tips for people starting in the field as to what would be the, I don't know, the first thing that you would recommend, say something to someone from physics or maths to learn in order to be able to start playing around with these architectures and implementing them? And because it's not by now only a matter of knowing deep learning, but also perhaps of knowing how to organize um, structured experiments that kind of go through a broad swath of different types of architectures. And I think that's a kind of a next level that you've been developing as well. And well, I guess also with Topo Benchmark. But maybe if you could just say, like, you should probably be understanding this first before you go into the field. What could you
I would just get your hands dirty immediately. Go play with Topo Benchmark. Go try to run an experiment. And it doesn't have to be like 55,000 experiments. Pick one model, pick one data set, and tinker around with it. We have hosted a couple challenges in the past asking people to implement their own model in a really structured, really like step-by-step, example by example way. And I think that has been really helpful to get people to feel more comfortable with the the actual implementation of these models. So definitely check out those challenges, and I would just try to run a single experiment, and I think through that you'll learn a lot.
Yeah, that's great. So it's an invitation for everyone interested. And we have a question by NPL Research. I don't know if you can read the chat, or do you want me to read it out loud?
Yeah, I don't see the chat. Sorry.
It says
Oh wait,
the
no, I got it.
latest. I'll just read it. It says the latest comparison of how much accuracy you keep with respect to model size. Did it include also the comparison with the normal GNN you used earlier, or was it between higher order models only? No.
That's a really good question. So we do have access to the normal GNN, but in no cases did it do as well as the higher order version. So we don't have it in the table because the table only considers the best performing model. So if the GNN was the best performing model, it would be in these rows, but that just wasn't the case.
Okay, that's great. I hope that answered NPL Research's question. And would anyone else want to ask anything, Mathilde?
I actually have a question regarding the table.
Yeah, absolutely.
Go ahead.
Like, I wanted to ask if there was previous work using combinatorial complexes, because as I can see there, like the best model on Topo benchmark does not include like the combinatorial complex.
Yeah. No. So combinatorial complexes were proposed by Hajij 3 years ago, basically exactly when I started my PhD. And he implemented maybe a few networks, but never really tested them. I'm not even sure if they're implemented somewhere. There is no currently like available experiments on the combinatorial complex domain. So we propose a model that has the theoretical machinery to accommodate combinatorial complexes, and that's why we can test on a bunch of different domains. But there is no like benchmark experiments on combinatorial complexes, if that makes sense. In part because of the lack of lifting. There's not really many liftings right now that can turn data sets into combinatorial complexes. That's like a very active research that I'm working on right now, actually, with some collaborators, is figuring out how to lift a data set into a combinatorial complex, not just a cellular complex or a simplicial complex or a hypergraph.
Okay, thanks.
That's fantastic. Yeah, those very good questions. Does anyone else have another question that they might want to ask Mathilde right now? I think in this context of liftings, maybe you could tell us a little bit more, or maybe even you could explain a little bit more just the idea of lifting, because sometimes this word lifting doesn't really exist maybe in the mathematical literature like that. It generally means something else. So maybe just going over again what this means in this context.
Yeah, absolutely. So a lifting is the map, mathematically speaking, that maps your graph object to some higher order complex. So in the process of lifting your graph, you have to figure out which complexes, which faces, which volumes, which hyperedges you want to draw, how you are going to decide what is a higher order relationship and what isn't, and also what features are going to inhabit these faces, right? My lifting is what determines the feature of my face. Is it just the sum of my nodes features? Is it the average of my edge features? I don't know, it could be anything. And the lifting is the map that will provide you with that information. So there's a lot of different possible liftings, and I think it's kind of a data set specific thing in terms of what will work and what won't, and a very open field of research in terms of figuring out the best way to map a graph to any of these objects.
Yeah, that's very fascinating. I mean, I think this is from my perspective, an area of opportunity for combinatorial topologists to interact more with this topological deep learning community and kind of go through all of the ideas that were behind the development of combinatorial topology, I guess last century. So I think this is exciting, and it's also an opportunity for more interaction, as Professor Millet was saying before. Once again, does anyone want to ask any other questions? Maybe one
Yeah,
last
I have
chance. Go ahead.
Yeah, there is this concept of n distance, multi-distance, and m metric that can compare more than two samples as traditional distance does. Basically, it allows you to create a predicate between n samples, in this case, n nodes from a graph, and determine if they can create an n cell of node or not. Maybe that could be helpful to create a lifting.
Absolutely. Yeah, absolutely. I would imagine that that could help create a hypergraph, actually.
Or a non-flag simplicial complex.
Mm-hmm. Absolutely. Yeah.
Yeah, and also this combinatorial complex.
Mm-hmm.
What is actually the main challenge with that kind of complexes? The combinatorial growth or something else?
Yes, absolutely. The cost associated to considering more relationships, but also just in terms of the lifting, figuring out how to implement in the software
Yeah.
hyper edges that have hierarchy to them.
Yeah.
It's not simple.
Yeah.
All of your adjacency matrices start to get really complicated. So
Okay.
figuring out how to do that properly is not trivial.
Yeah. A question could be, for example, in this combinatorial complexes, a combinatorial cell can be understood as a power set or as a subset of a power set.
Yep.
Okay, because
Yeah, that's the definition.
okay, there is a implicit data structure, not published, but can give you the n set of a power set without generating any of the n-1 sets. So you can pick directly the set that you want just for the final set. So maybe with those kind of ideas, maybe this combinatorial complex can be implemented.
Absolutely. Yeah. No, I love it. Thank you.
Thanks.
Yeah, thanks for all of those questions. I mean, this problem of liftings is a very active field of research, and as Mathilde mentioned, there was even an entire challenge on it. And I think, as she also mentioned, there's like a push towards standardification of both notation and techniques. So yeah, we encourage everyone to keep participating. We should probably end the recording for now, and I would ask the recording folks to help us stop that.